Okay guys, here I will discuss common emitter input characteristic of Npn transistor. Now first we define input characteristic of a transistor. Basically it is a graphical relation between input current and input voltage by keeping output voltage constant. Like if we plot a graph between input current and input voltage and keeping output current constant, then this is called input characteristic of a transistor. Now here I have this NPN transistor. This is collector, this is base, and this is emitter. Because the width of collector is higher than base and emitter. Base is thin and emitter is moderately, like it is a intermediate width. Now in common emitter we take emitter common between collector and base. So here this is the emitter, so I'll keep it common between emitter and between base and collector. So now this is a 4-terminal device now, so I have to apply input here between base and emitter, and I will get my output here between collector and emitter. So this is junction J1, this is junction J1, and this is junction J2, and the transistor is always operating in active mode. And we know that in active mode, junction J1, which is the junction between emitter and base, or between base and emitter, is always forward bias. And junction J2, which is the junction between collector and base, is always reverse bias in active mode. Is always reverse biased. So in order to make this junction J1 forward bias, we will connect base to the positive terminal of the battery and emitter to the negative terminal of the battery, because base is P type and emitter is N type. So this is now a diode. Okay, so we have to make it forward bias. So in order to make a diode forward bias, the P side of the diode is connected to the positive terminal of the battery, and N side of the diode is connected to the negative terminal of the battery. Now this battery I call it VBB. This is the battery VBB. Now here we will apply the input, and we will get the output here. Now in order to operate this transistor in active mode, the junction J2 will be in reverse bias. So in order to make this junction J2 reverse bias, we connect the collector to the positive terminal. Okay, the collector to the positive terminal, so the other terminal will automatically be negative. So this junction is now in forward bias mode. So here the voltage between base and emitter, the difference in voltage appear between this base and emitter is represented by VBE. Why I put base first and then emitter? Because the terminal which is connected to the positive terminal of the battery always come first and the negative comes later. So here base is connected to the positive terminal, so that's why I put B first, and then emitter is connected to the negative terminal, so that's why I put emitter later. Now here, if I look at here, then collector is connected to the positive terminal and emitter is connected to the negative terminal. So the voltage appear between this collector and emitter, or the voltage difference between collector and emitter, is represented by V. I will represent it by VCE, because collector is connected to the positive terminal and emitter is connected to the negative terminal. Now this is NPN transistor, so the emitter current is always outside. This is the direction of emitter current, while the base current and collector current will be inward, IC, and this is IB. So here the input current is, so here in this case the input current is IB, because I already mentioned it in the common emitter characteristic of a diode. Now the input voltage will be VBE. The output voltage and output current will be IC, because the collector current will be output, and the output voltage will be VCE. So the common emitter input characteristic can also be defined as the graphical relation between input current, which is between input current, which is IB, and input voltage, which is VBE, by keeping output voltage constant and output voltages by keeping VCE constant. Now this is called common emitter input characteristic. Emitter input characteristic. Now here I will draw a graph between input voltage, which is VBE. This voltage will be measured in volt, and the input current is IB, and we know that the base current is very, very small. That's why we measure it in the unit of microammeter. Now as we see here, the junction J1, emitter base junction, it is a forward bias junction, and we gave it given the input current and input voltage between this junction. I cross this junction. So if I keep my output voltage VC, if VCE is equal to 0, like if I disconnect, there is no biasing of this junction J2, and this junction J1 is forward bias, then this looks like two diodes which are connected with each other. This is like this. So here we have N, this is P, this is N, this is P. So this diode is already, it's not connected, so it's not in active mode, and we had connected these diodes only. So it means that the relation between voltage and current of this diode is similar to that of forward bias. Okay, so if Vc is equal to 0, then in case of forward bias, if we have a diode which is acting in a forward bias mode, then we have this relation. The relation between current and voltage is like this. Like if the voltage is below the knee voltage, like its value is 0.7 or 0.3 electron volt, okay, for silicon, for germanium, then there is no current flowing in this diode. But as we increase the voltage above this value 0.71, then there is a abrupt change in the current. The current varies like this. This is what we call it the forward bias diode characteristic. So the same will be true here, because if we keep outside voltage, like the output voltage Vce is equal to 0, what it means? It means that if we are not operating, or this junction J2 is not operating, it is not connected to any kind of battery, then the current flowing through this diode, through this junction, it's look like the current through forward bias diodes. Okay, and in case of forward bias diodes, we have the output, the relation between the current and voltage is like this. This is the knee voltage. Okay, this is the knee voltage, or the threshold voltage. Okay, VTH. Like if the value of this input voltage VBE is below this threshold value, which is 0.7 for silicon and 0.3 for electron volt for germanium, then there is no current. Through the junctions. But as we increase this voltage, this input voltage above this value, then the current abruptly changes to like this. Now this is for the case when the output voltage is 0. Now if I increase the output voltage from 0 to, let's say, 1 volt, like if we increase VCE, the voltage between the output voltage, from 0 to 1 volt, then what will happen? Then we have, the situation is like this. The graph is, I will use a different color per point now. The graph is like this. So there is a decrease in the base current as we increase the output voltage, and the reason behind this is the early effect. Because in early effect, we already discussed in class there. We already discussed in the class that if now there are two junctions now, because this is a NPN transistor, so we have two junctions. So I will just, this is junction J1. Okay, this is J1 and this is junction J2, and this is the NPN transistor. Okay, NP. This is base. Sorry, this is emitter. This is base, and this is collector. Now this junction J2 is forward bias. So it's forward bias. So it means that we have connected this So it means that if it is no sorry, this junction J2 is reverse biased. It's reverse biased because inside of this junction diode, this inside of this junction J2 is connected to positive terminal, so it is forward reverse bias. So if it is reverse bias, so it means that the depletion layer here, if we increase the voltage, okay, then the depletion layer or the junctions here is getting bigger, but the depletion layer is more penetrated in the base as compared to the collector. So if this is the case, then now the initially the junction width was this one. This was the width of the junction WB. Sorry, this is the width of the base. Now if we increase the voltage across this junction J2, then what will happen? The junction here, it goes more penetrated in the base as compared to the collector. So this is the junction area now. So the net base width left here is now this one. This is called effective width. This is the effective width, and this is the width of the junction now. Now if I look at here, then the width of the base width is equal to effective width plus width of the junction. From this I can get my effective width, which is equal to width of the base minus W. Now if we look at here, if we increase VCE, if VCE is increasing, then what will happen? This W also increases. Then the width of the junction W also increases. So if W increases, implies that what will happen? W effective will decrease. This implies that W effective width, or the width left after making the junction J2 forward bias, reverse bias, sorry, will decrease, because if this is increasing, then there is a negative sign, so this dW effective will decrease. Now the width of this base region is now decreasing. So suppose initially the width was this one, now the width left is this one. So this implies that what will happen? Now if W effective decreases, then the electrons coming from the emitter to the base, so if electron is coming from emitter to the base, then there is a less recombination of electron with holes in the base region, because we have less holes here now as compared to this case, because the width is decreasing. So here we have, if initially I have, let's suppose 10 holes here, now if the width is decreases, the width is decreasing, then I left only 3 holes now. So only 3 electrons will recombine here. In the initial case, 10 electrons will recombine if the junction is not forward reverse biased. But now the junction is reverse biased J2, so if only 3 electrons will recombine, while rest of the electron will goes to the collector. So it means that the collector current IC will increase. So if collector current is increasing and there is less recombination of electrons and holes in the base region, so the base current will decreasing. So that's why we say that as we increase the output voltage VCE from 0 to VCE 1 volt, then the base current is decreasing. If I further decrease the base current, let's say from 1 volt to let's say 2 volt, then the graph will looks like this. This is for 2 volt VCE, because now due to early effect, the width of effective width will further goes on decreasing, and if effective width is further decreasing, then there will be a less recombination of electrons and holes in the base region. So if there is a less recombination of electrons and holes in the base region, which implies that the base current is also getting smaller. So this is all about the input characteristic of the common emitter input characteristics. Now here I will derive only the I will use the relation for the what we call it, the resistance or the input dynamic resistance. Okay, now the input dynamic resistance Ri, because we know that from Ohm's law that V is equal to IR. If I calculate my resistance IR, R will be equal to V over I. Now the input resistance or the dynamic input resistance of common emitter, okay, CE means common emitter, is equal to change in voltage, input voltage, sorry, delta V BE over change in current, delta I. Input voltage or output current, input voltage or input current will give us the input resistance. Now this is the dynamic input resistance, and by keeping output current VCE is equal to constant, because we keep output current VCE as either 0 for the whole case, or we keep it at 1 volt, or we keep it 2 volts. So VCE or the output voltage is taken constant here. Now in case of common base characteristic, the input resistance was for the common base. We already derived this relation there, VBE over delta IE, and VCB, the output voltage, is constant. This is for the common emitter case, and this is for the common base case. Now we know that emitter current is much bigger than base current. So it means that if emitter current is much bigger than base current, then this quantity is smaller, because this emitter current is bigger, and this quantity will be bigger because the base current is smaller. So this implies that delta IE will be much greater than delta IB. So if this is the case, then from there we can say that from this equation, it means that if we divide something with a smaller quantity, we get a bigger number. If we divide something with a bigger quantity, we get a smaller number. So this will be bigger as compared to this one. So the input resistance or the dynamic input resistance in case of common emitter case is higher than the dynamic resistance in the case of common base characteristic. So this is all about common emitter input characteristics. In the next video I will discuss the common emitter output characteristic of NPN transistor. Thank you.